Welcome to the solutions video for assignment 3.04, number 3. So that's questions 7, 8, and 9 from topic 7.5. In question 7, we've got someone who has made some investments. He's looking to make $25,000 off the original $15,000, and we've got the track for how much it is per year. Now this time we're asked to do the regression twice. Once as an exponential regression and once as a logarithmic regression. So we have to take a look at our data and figure out which is on the x-axis and which is the y in order to make this happen. Now, any good investment will grow exponentially. So we're going to start with our scatter chart. We're going to customize. Now this isn't looking super nice because the spreadsheet here doesn't do that zoom fit as nicely as our calculators do. But here we have a nice clean exponential function. To get it to show a little more clearly, I'm going to take our vertical axis and make our minimum value that 15,000 we're starting with. We want our max at 25. And for our horizontal axis, right, let's keep our minimum value at 0, but let's make our max 10. It looks like we're going to need more than 10 years to get to our 25,000. There we go. So here is the data plotted with all the data that we're going to be looking for in the long term. So question 1, what's the equation of the exponential regression? We have that here. It's 15,000 times e exponent 0.044. Now, e to the 0.044 is roughly 1.045, which is what theory tells us it should be for a 4.5% interest growth. Now, we're going to skip to part C, or no. Yeah, part C here, use each equation to determine what time it takes for the balance to equal 25,000. So part C, we have to look for that intersection. We can do that on Desmos. We have 15,000 times 1.045 to the x. And we're going to change our x and y to be the same. We're going to make our x go to 15. And our y is going to go from 15,000 to, we'll make it 26,000, so the 25,000 fits. Y equals 25,000. There's our intersection. So this is one where we have the y, we have to solve for x, and it's about 11.6 years, or 12 years if the interest is being compounded annually. Now we were also asked to find the logarithmic version. So we could do that by reversing our x and y axes because it is the inverse, which means we need our x to now go from 15,000 to 25,000. And we need our y-axis to go from 0 to 15. And we need to change our series. Our trend line has to go from exponential to logarithmic. And now we get a decent fit. So this equation, the negative 218 plus 227 log x, that is, so I think it was a negative 218. Yes, negative 218 plus 22.7 log x. So this one is not appearing because, again, we have to reverse our axes here. 15,000, 26,000, and 0 to 15. Now we can see our graph. And to find the point where x equals 25,000, we intersect at roughly the same point. Here it's 11.9 instead of 11.6. It's still 12 years if we're doing it in whole number years. That little bit of variation is just because we are rounding, or these numbers that are displayed here are rounded to a certain number of decimal places. If we went past these number of decimals, it would work. And the final question, which equation would you prefer to use? I think most of us are going to prefer the logarithmic equation to the exponential, because the logarithmic equation allows us to just plug in 25,000 as x, whereas using the exponential by hand, we have to do a lot more algebraic manipulation to get there. So the value we're trying to hit is the x value that we put in with our logarithmic fit. That's the advantage of doing the logarithm. Now, in our next one, we are looking at the distance modulus and the distance from Earth. So it's the difference between the apparent brightness and its brightness when measured from a distance of 10 parsecs. 1 parsec is, it's roughly this number. The definition we can get into if you want to. It's what we call parallax. So things that are close to you that move 1 centimeter go through a bigger portion of your vision than things that are far away from you that move 1 centimeter. That distinction is parallax. Things move more against the background when they are close to you than when they are far from you. And degrees are further subdivided into minutes of arc and seconds of arc. So 1 second of arc is 1 out of 3, or 1/3600th of a degree. So a parsec is how far away you need to be from our solar system before the arc, the parallax arc of Earth's entire orbit, takes up 1 second of arc. So it's a parallax second, and that distance is 3.09 times 10 to the 13 kilometers. That's how far away you have to be before the entire breadth of Earth's orbit is 1/3600th of 1 degree of the arc in front of you. Anyway, we have our distances and we have our distance moduli. Here we need to identify our independent and dependent variables. Well, the distance from Earth comes first and the modulus comes second. So the distance should be our independent variable. That should be our x. So if we want to create the scatter plot that way, we'll do that with sheet 2. So we're going to insert a chart. We're going to make it a scatter plot here. And there we have the distance from Earth on the x and the apparent modulus on the y. So we have completed that first portion of the assignment. Now we have to use this data to determine the regression equation, the logarithmic, to get the distance modulo m as a function of the distance from Earth d. So this tells you later on that distance from Earth d should have been your x. That's right in part C. So we are going to come in, again, pick our trend line, use the logarithmic plot, and pull up our equation. So here is the equation that describes our modulus. Oh, sorry, that's not the window I wanted to go back to. It was this one. So Wolf 359 is considered to be the 5th closest star to Earth at 2.39 parsecs. Determine its distance modulus to the nearest hundredth. So that's an x of 2.39 parsecs, so 2.39 times 3.09 times 10 to the 13. So 2.39 times 3.09 times 10 to the 13 gives us 7.3851 times 10 to the 13. And we just need to calculate that. We could do it with intersections on the graph. We could actually just do it with the spreadsheet now that we have our equation. So we could say negative, there it equals negative 5.09 plus 2.17 times the natural log of 7.3851 0.3851E13, and we get a distance modulus of about 64 with this fit. So then finally, Gliese 876 had 4 known planets in 2001 and a distance modulus of negative 1.66. Determine the distance from Earth. So here we're doing it in reverse. So we can do that by working in reverse. Our distance modulus is a negative 1.66. So if we take our negative 1.66 and add 5.09 by bringing that across the equal sign, we take that and we divide it by 2.17, and then we take the exponential of that number. That gives us our distance. And I think now that I look at it, this would have been the distance in parsecs. So I think for the first one where I had the 64, I don't think we needed to convert. I think that should have just been the 2.39 and given us a distance modulus of negative 3.2, roughly. Because with these scales, that has to be the distance in parsecs. So yes, Gliese is about 4.86 parsecs away. And answer to the nearest tenth is 4.9. Okay, and let me just double check that here. Yes, this distance was in parsecs, so I did do the first part wrong initially, but that has now been corrected. Finally, question 9. In February 2004, Mark Zuckerberg launched Facebook from his Harvard dorm room. And then this is how quickly the user base has been growing. So we want to create a scatter plot. Again, this is really one set of data, just broken into 2 columns so it all fits together. So we want to create the scatter plot, do it in the logarithmic regression for a function of time, so the number of months, as a function of the number of registered users, which means the number of registered users, n, is our horizontal axis. Again, the data with the greater variation should be the horizontal in a log plot. And interpolate to figure out when it first passed 275 million registered users. So interpolate is find the value in or between the data points you already have to find that 275 million mark. So we are going to do this in 3 stages. That's why it didn't work. I had the wrong one selected last time. Okay. So again, we want the millions of registered users to be our x-axis. So I'm just going to flip our data set around, which is something the spreadsheet allows us to do, so that when we graph it by default, our x and y are there, and it looks like a logarithmic plot. We will customize the series by putting in our logarithmic trend line, using the equation as a label. So there's our equation. 3.89 plus 11.1 times the natural log of x. And then our last step is to interpolate, find when we hit the 275 million registered user mark. We can do that just by plugging in 275 as x in that equation. And we get that it took about 66 months from when it launched in February 2004. So 5.5 years. So we are looking at August of 2009 by the time it reached that point. So this concludes the homework assignment 3.04, number 3.